Good morning. We have discussed the unilateral Laplace transform of the function. Now we'll discuss the inversion of the unilateral Laplace transform. For the unilateral inversion of the unilateral Laplace transforms, so understanding the concept of the counter integration, it is very difficult. So another method is we have to have the one-to-one relationship between the signal and its unilateral Laplace transform. If you have the knowledge of the several basic transform pairs and the Laplace transform properties, then we can use the Laplace transforms and we can easily find the inversion of the unilateral Laplace transforms. So in a linear time invariant systems, which is described by the integral differential equations, inversion of it is unilateral Laplace transform. Okay. Inversion of unilateral Laplace transform. So we'll generally in linear time invariant system, which is described by integral differential equations, we generally encounter Laplace transform that are a ratio of polynomial polynomials in S, ratio of the polynomials in S, and therefore the inverse transform is obtained by expressing x of s as a sum of terms, as a sum of terms using a partial fraction expansion Okay, so suppose x of s is given b of s by a of s. Okay, these values are given if it is expressed in an exponent in the ratio of the polynomials. So b of s, it is a bm s raised to power m plus b m minus 1 s raised to power m minus 1 plus b1 s plus b0 divided by s raised to power n plus a n minus 1 into s raised to power n minus 1 plus a1s plus a0. Okay, so here if x of s is an improper rational function, is an improper rational function. So if it is improper rational function, that means the m is greater than or equal to n. Then we may use long division to express x of s in the form. Then we may use long division to express x of s in the form x of s is equal to summation k equal to 0 to m minus n ck s of k plus x of x tilde of s. So if x of is an improper rational function, that means the m is greater than or equal to n, then we may use the long division to express x of s in the form. So x of s is equal to summation over k equal to 0 to m minus n ck s raised to power k plus x of s tilde. So where this x of s tilde is x of s tilde is equal to b tilde b of s tilde over a of s. Okay. So the numerator polynomial is here b of s. This numerator polynomial has this numerator polynomial b of s has now order 1 less than that of the denominator polynomial. And now the partial fraction expansion method is used to determine the inverse Laplace of x of s. Now partial fraction expansion is used to find the inverse Laplace x of s tilde. So given the impulse and its derivative, the impulse and its derivative are 0 at t equal to 0 minus. Okay, this initial condition. So given the impulse and its derivatives are 0 at t is equal to 0 minus, and therefore we find the Laplace transform we find the inverse transform of the terms in the some components of x of s, like this summation k equal to 0 to m minus n c of k into s of s raised to power k, using the pair that impulse response del of t, which unilateral Laplace transform is equal to 1, and its differential property and the differentiation property d of dt x of t unilateral Laplace transform is s into x of s minus x of 0 minus. Okay, so we obtain now summation k equal to 0 to m minus n ck del of del raised to power k, that is del of t unilateral Laplace transform, that is summation k equal to 0 to m minus n ck s raised to power k, where del of t denotes the del k of t denotes the kth derivative of the input, of the impulse del of t. Okay, so now we factor the denominator polynomial. We factor the denominator polynomials polynomial as a product of full factors to obtain, therefore x of s tilde is equal to bp s raised to power p plus b p minus 1 s raised to power p minus 1 some plus up to b1 s plus b naught divided by this product over k equal to 1 to n of the terms s minus d k. So where this p is less than n here. So if all the poles dk are distinct, if all the poles dk are distinct poles, then we can use the partial fraction expansion. We can express it by partial fraction expansion. We may rewrite x of s as a sum of simple terms. So x of s tilde in simple form we can express here summation k equal to 1 to n this a k by s minus dk. So here ak is determined by using the method of residues. Okay, ak is determined by using the methods of residues or by solving a system of linear equations. Okay, so therefore the inverse Laplace transform of each terms in the sum may now be written like this. So what is the inverse Laplace transform of this? A of k into s minus dk. So this is the unilateral Laplace transform of this is. So the 1 upon s minus dk. What is the inverse Laplace transform of this? E raised to power dk into t into u of t, and this ak will also come here. Okay. So this is the pair. So resulting in a pair like this. Okay. Now if suppose a pole is repeated, if suppose pole suppose d is repeated, pole d is repeated r times, then there are r terms in the partial fraction expansion. Then there are r terms in the partial fraction expansion. And we can write by the r term means this is ai1 by s minus d I. Second term ai2 by s minus di square e divided by s minus dk raised to power r. Dk raised to power r. Okay. So the inverse Laplace transform of each term is found, and we can write here like this. E over s minus dk raised to power n. Then what will be the pair of this corresponding in the time domain? So e raised to power del k3 into u of t e t raised to power n minus 1 by n minus 1 factorial. So this is the inverse Laplace transform of the repeated poles. Okay, so by using such pairs, basic Laplace transform pairs and the Laplace transform properties, we can find the inversion of the unilateral Laplace transform. So we'll consider one example. X of s is equal to 3s plus 4 divided by s plus 1 into s plus 2 square. So here this is one distinct pole is there at s is equal to minus 1, and this is a repeated poles. Repeated how many times? 2 times. So therefore we can also expand this. We can also expand by using the partial fraction, and therefore solution a partial fraction of x of s x of s, that is a1 over s plus 1 plus a2 over s plus 2 plus a3 over s plus 2 square. Okay, we can expand the given function like this. Now we have to solve for this a1, a2 and a3. Solve for a1, a2 and a3. I will directly write this value of the a1, a2 and a3 because we have already solved such type of the coefficients a1, a2 and a3. So here the a1 is here 1, a2 is here minus 1, and a3 is here Therefore, we can find these residues by using the partial fraction expansion. Okay, we already solved this such type of the example in the previous problems. Therefore, I have written here directly. So x of s, we can write this value in the given equation. This is minus sign minus 1 over s plus 2 plus 2 over s plus 2 square. Okay, now we have to use the basic Laplace transform properties, and we may construct this x of t. We may find the inverse Laplace transform of each terms in the partial fraction expansion as follows. The pole of the first term at s is equal to minus 1. This is a pole at s is equal to minus 1. So we can write the pair for this. It is 1 over s plus 1 in the s domain. Okay, so unilateral Laplace transform. So what will be its corresponding function in time domain? So s plus 1 means e raised to power minus t here, and this is u of t. That is unity function. So e raised to power minus t into u of t. The Laplace transform of this is 1 over s plus 1. So this is the first term. Similarly, we can write for the second term also. What is the second term in the equation? The second term has a pole at the second term has a pole at s is equal to minus 2. Therefore, we can write here the this is a second term 1 over s plus 2, and it has a pole at s is equal to minus 2. So here e raised to power minus 2t into u of t. Okay, so this will be, and here sign is positive. So no negative sign is there. Okay, in second term negative sign is there, that's why we are taking here negative sign. Otherwise, rest of the factor is just like this. Rest of the factor is like this. E raised to power minus t, here e raised to power minus 2t. So this 2 is appearing here. Okay, same Laplace transform, but because here we have the minus sign will appear here. So inverse Laplace transform of this is minus e raised to power minus 2t into u of t. And now come to the third term, that is a double pole. The repeated pole in the last term at s is equal to minus 2, and therefore we can write here its pair in time domain and s domain. So 2 over s plus 2 square. Okay, 2 over s plus 2. So again we have to write same here, e raised to power minus 2t into u of t. Okay, as here 2 is there, that's why we have to write here 2, and as square is there, so instead of square it is a 2 here. If suppose it is a 3 is here, instead of 2 here it is 3, then here it will be appear t square like this. Okay, so as there is a square in this case, so we can write here 2t e raised to power minus 2t ut into this. So this is the pair, and now we have to combine all the three terms, and we can write here x of t in time domain is equal to the first term, that is e raised to power minus t into u of t minus e raised to power minus 2t into u of t plus 2t e raised to power minus 2t into u of t. So this is the inverse Laplace transform of the given function. Okay. Thank you very much.